Welcome to EDU World Space.
So we're given that aluminum wire has a diameter of 2.14 millimeters, or 2.14 times 10 to the minus 3 meters. And we're also told that a copper wire has the same resistance and length as the aluminum wire. So that is, so to distinguish between the resistance, I just put Cu for copper and Al for aluminum. So this equation says that they have the same resistance, and this equation says that they have the same length. And we're asked to find what diameter of the copper wire will satisfy the same resistance and length of aluminum wire with a diameter of 2.14 millimeters. So I'll actually solve this on the next page. And we will use equation 25.10, which tells us that the resistance is the resistivity times the length over a cross-sectional area. And then we'll use the resistance of copper is equal to the resistance of aluminum, because we're told that both we want to find the copper wire with the same resistance as the aluminum wire. So if we substitute this portion into this equation, then we find that the resistivity for copper times the length of copper divided by the cross-sectional area of copper is equal to resistivity of aluminum, length of aluminum, over cross-sectional area of aluminum. But we're also told that they have the same length. So that means that we can get rid of these two lengths because they're the same. So then we find that the resistivity of copper over the cross-sectional area of copper is equal to resistivity of aluminum over cross-sectional area of aluminum. And I got this by simply canceling out these two because they're the same length. And now, remember that the cross-sectional area is corresponds to a circle, so it's pi r squared, which is 1/4 pi d squared, where d is diameter, and I just use that the radius is half of the diameter, so that when you square this, you get 1/4 d squared. So we'll use this in just a second, so let me just focus on this equation a little bit. So from here, let me rewrite it. So from this equation, you can find that the cross-sectional area of copper is equal to the resistivity of copper divided by the resistivity of aluminum times the cross-sectional area of aluminum. And then now I will plug in the area. So we have 1/4 pi d squared for copper, which is equal to resistivity of copper over resistivity of aluminum times 1/4 pi d squared, of aluminum. Now, this factor is common to both sides, so we can immediately cancel them out. And then we have d squared copper is equal to resistivity of copper over resistivity of aluminum times diameter squared of aluminum. And you simply just take the square root. So you can find the diameter of copper, so that will be the square root of resistivity of copper over resistivity of aluminum times the diameter of aluminum. And let's put in the numbers on the next page. So we have 1.72 times 10 to the minus 8 ohm meters for the resistivity of copper, and the resistivity of aluminum is 2.75 times 10 to the minus 8 ohm meters. So I use table 25.1 to get these values, and we were given the diameter of aluminum, so that is 2.14 times 10 to the minus 3 meters. And if you plug these into your calculator, then you find that the diameter of a copper wire needs to be 1.69 millimeters.